The topic for this week is independence. So we will further go into the notion of independence. It will talk about independence of events, independence of random variables. So before we start the concept of independence, which you have seen before, I just want to remind you about conditional probability definition. Suppose you have a sample space omega, two events A and B, it should be element of the power set of omega. So it could be a sigma field, but let's just assume that 2 to the omega is the set of all interesting events. If this is the case, then probability of A given B is defined to be probability of A intersection B upon probability of B. So you should think of this as probability of A given that event B has happened. Given this definition, we defined two events A and B, again element of the power set of omega, to be independent if and only if this condition holds true. The probability of both happening is multiplication of probability of A and probability of B. So this we took as the definition of independence. This definition is closely related to a more intuitive definition, which is that probability of A given B is equal to probability of A. So this is more intuitive because this says that knowing that B has happened does not affect the probability of A. We saw that these were almost equivalent except a boundary case, and I will just leave it as an exercise for you to remember or figure out why these are not exactly equivalent but almost equivalent. So this was the definition of independence. A very closely related concept is the negative correlation or positive correlation of the independence. So what we saw in the independence was that if two events do not affect each other, then we believe that probability of A intersection B should be probability of A multiplied by probability of B. The events are said to be negatively correlated if the probability decreases than what is expected. So other way to think of it is, if we know that A has happened, then the chances of B happening decreases. In a very similar way, we can define positive correlation, which is probability of A intersection B greater than B. So these are the formal definitions. Intuitively, negative correlation means given A, probability of B reduces. And the opposite case for the positive correlation. So two events are linked in a positive sense. If they are positively correlated, they are linked in the negative sense. That means occurrence of one affects negatively on the occurrence of second. Then they are negatively correlated. So let's look at some of the examples. We will start with some examples so it is quite clear whether things are independent or not. We toss two coins, and then A is the event. That first coin is heads, B is the event, second coin is, and it's intuitively clear that since the first coin toss has nothing to do with the second coin toss, these two events are independent. You can easily verify it using formula also. We won't go into that. But this could be generalized. If A is an event which only depends on first coin toss, again it is not completely defined, I'm just saying vaguely that A is some event which only depends on first coin toss, and B only depends on the second one, then A and B should be independent. Actually, many a times this is given in the definition of the problem. So when people say that we toss two coins independently, they are basically saying something like this, that the first coin toss does not affect anything in the second coin toss. So this is how it is stated in many problems. This is quite a clear example of how two events can be dependent. We can take second example. Let's say we have a pack of cards and you pick two cards one after another. And the question is, let's say A be the event that first one is an ace, B second one is an ace. Question is, are they independent? Are events A and B independent? So if you remember our previous discussion, it is very important to realize whether the picking is done with replacement or without replacement. With replacement, your guess should be A and B are independent. Without replacement, then A and B are dependent. An intuitive way to see it would be that if we are doing this experiment without replacement, the first pick is an ace. Now the number of aces have reduced to be just 3 in the pack. So in the next iteration, chances of having an ace have, so definitely they are dependent. Again, this was an example where it was kind of clear that the two events were independent. The third example would be any sample space. Suppose A and B are disjoint events. And again, intuitively, once I know that A has happened, then probability of B is 0. So probability of B given A is 0. Knowing A gives me complete control over B, so they cannot be independent. So these two events are dependent. As an exercise, again, there is a special case when two disjoint events are independent. You need to find that special case. This, I leave it as an exercise. Let us take another example. We toss two coins, not stated anything, then we assume that they are unbiased. Let A be the event that first coin is head. B is both outcomes. Now in this case, it is not clear that they are independent because is not entirely dependent on the second toss. So we can't clearly say whether the two events are independent or dependent. In any such case, we use the definition. So probability of A is half. Probability of B again you can calculate is half. And probability of A intersection B means the coin toss was head and head, which happens with 1/4 probability. This implies that probability of A intersection B is PA times PB. So A and B are. So this tells us that whenever in doubt, we can use the formula to verify whether two events are independent or not. Let us take another example, a slightly complicated one. Suppose someone wants to find out whether the occurrence of two diseases, asthma and diabetes, are related or not. To check this, they go to a hospital which has only two kinds of patients, asthma and diabetes, and then they calculate two things. The first is the probability of a general person having asthma. So this is the probability of a general person having asthma. For this, they look at the fraction of people in hospital having asthma. So this is the first quantity which they measure. And then the second quantity is probability of a diabetic person having asthma. And again, for that, they go to this particular hospital and calculate fraction of diabetic patients having asthma to calculate this property. So they calculate these two quantities and they see that probability of a diabetic person having asthma is much less than general person having asthma. Should say chances. So they conclude it is better to be diabetic if you want to avoid asthma. Continue. This statement is in front of you. What do you think? It should be quite clear to you that the consequence seems unlikely. And as a student of probability, we should be able to figure out what has gone wrong. Why is this conclusion false? So pause the video, think about it and see if you can find out the correct reason why this conclusion is false. So let's see why this conclusion is false. We will see that if we just express everything clearly in terms of our probability framework, we'll find the error. So define two events, A being person having asthma, D being person having diabetes. So what we want to find out is whether probability of A intersection D is equal to probability of A multiplied. The reason why the conclusion is false is because of a simple reason. They did their survey in a hospital and not general population. So what do I mean by that? So let's see what quantities they calculated. The first quantity they calculated was fraction of people having asthma in total number of patients. So that is probability of A, not really just probability of A, but probability of A given patient has either asthma or diabetes. Because they are in a hospital, there are only patients there. So this is the quantity which they are calculating. What about the second quantity? They calculated people having asthma and diabetes among diabetic patients. There's probability of A intersection D given diabetes. And you can convince yourself that this is also probability of asthma given diabetes. So just to falsify the conclusion, we will see that actually if A and B are independent, that means they satisfy the condition, even then this quantity is going to be less than the second quantity. And that will explain the conclusion to be false. That will say that why this paradox was appearing. We were supposed to find out relation between A and D, but we are calculating them as this and this quantity, and that will show that why this false conjecture has been obtained. We are comparing two quantities. One is probability of A given A union D. This was the first quantity. This was our estimate of fraction of people having asthma. Fraction of people having asthma in general population. The other quantity is probability of A intersection D given D, which was also the same as probability of A given D. So this was our estimate of people having asthma when they are also diabetic. This is the general population and this is diabetic population. And in both of these, we are calculating number of people having asthma. And now by law of conditional probability, this is divided by probability of A intersection D, and I want to compare it with probability of A given D, which is probability of A. This follows because A and D are independent. Now this simplifies to probability of A given probability of A union D. This I want to compare with probability of A. And now it is quite clear that this quantity is bigger. So even though A and D were independent, since we looked only at the people having asthma or diabetes, this quantity became bigger. So our estimate of people having asthma in general population was completely. Their conclusion was that these two events, A and D, were negatively correlated. They wanted to say that probability of A intersection D is less than probability of A, less than probability of D. Though what they measured was in a hospital, so they got that probability of A intersection D is less than probability of A intersection D, probability of D, A union D. So what we are going to show in the exercise is that even though A and D were independent, they were not negatively correlated. If you only look at the universe as being A union D, they will appear to be negatively correlated. There is again a special case when this could be equality, but in most of the time, this will be negatively correlated. And this you will prove as an exercise. And again, this tells you why the paradox was arising. In the general population, it was true that A and D were independent, they were not negatively correlated, but if you look at a special population, they might seem to be negatively correlated. But the truth is not that. This in literature is known as Bergson's paradox. We move to another few definitions. We want to define independence for family of events. So let's assume that instead of having two events, now we have a lot of events. By the way, this notation means this set AI where I belongs to I. So we have, let's say, these sets, then we can tell them to be so we have some set of events and we want to define whether they are independent or not. It turns out that a single definition is not good enough. So let's look at a few natural definitions. The first natural definition is these family of events being pairwise independent. This says that if you look at any of the two events, they are independent. This seems very intuitive. So a family of events is independent or pairwise independent if you pick any two events in the family, they are turning out to be independent. they do not relate to each other. Let's look at a slightly stronger definition, which is called mutually independent. So a family of events is called mutually independent if you pick any subset of the family, it turns out to be independent. That means for all subsets J, if I look at this event, that means all the events in the subset happening, this is just the multiplication of probability of. So in some sense, pairwise independence just forces the independence in between any two events. In mutually independence, the criteria of independence is applied to all possible subsets. So it is quite clear that if events are mutually independent, then they are pairwise independent. How about the reverse? Intuitively, it seems that if any two events are independent, that means they do not affect each other, then all the events should not affect each other. Again, pause the video and think about it. What do you guess? Are these two equivalent or are they not? It turns out they are not equivalent. And let me show this by an example. That's the best way to show it. Before I show you the example, realize clearly that mutual independence is a much stronger criteria. If events are mutually independent, they are definitely pairwise independent. We are asking the opposite question. If the events are pairwise independent, can we say that they are mutually independent or not? So we take a very simple case. Again, toss of two coins, unbiased. Let me define three events for toss of two coins. A is two tosses. We kind of looked at this event before also today. B is first coin toss is head. C is second one is say head. So the question is, are these events independent? Are they pairwise independent? Are they mutually independent? So let's first look at the easier criteria to check, which is pair. So what about B and C? It's pretty clear that they are independent. B depends only on the first coin toss. C depends only on the second coin toss. So they are independent. What about A and B? This is something we did today in the class. We know that they are independent. By the same logic, A and C turn out to be independent. So this implies A and B and C are pairwise independent. Are they mutually independent? So you will show in the assignment of this lecture that they are not. And one intuitive way to check it is, if B and C have happened, implies A has definitely happened. Right? So B does not give us any information about it. C does not give us any information about it. B and C individually give no information about A. But together they imply A. So in this sense, A and B and C are not mutually independent. We get that pairwise independence need not imply mutual independence. In the next lecture, we will see these concepts even for random variables and show an application in the field of computer science. Thank you.